You should have stuff for me. Chapter 2, sections 1 and 2. A little more of our propositional logic ideas. With an average of almost 80, I was a really easy grader. You all know what the hell you're doing. I know I'm not an easy person. Therefore, very well done. I am a little disappointed that you all didn't read the entire set of directions. Only half of you did, but now we know. If you've got questions, the key is posted to Canvas. Come talk to me. I'd be glad to discuss the exam with you. Meanwhile, Friday we had a recorded setup. I'm going to use that today as I move on in chapter 2. So, one of the interesting ways to look at a sequence is actually to think of it as a function. A sequence of elements from a particular set, S, can be thought of as just an ordering placed on that set. So I have a first, a second, a third, a 70/12th, whatever number order you want to use, right? Or I can think of it as a function from n. What was n again? The natural numbers. Again, there's some debate as to whether or not to include 0. If I did, I would have the 0th element, the first element, the second element. Again, an ordering of my things. And as a function, I have this sort of behavior. Where Si is an element of the set S. More often than not, though, we'll use A for an element. So AI is the ith element in the sequence A1, A2, and so on. Notice in that version, I didn't have an A0. This again is where that debate on what really is the start of the natural numbers comes up. Almost always when I am dealing with a sequence, I will need to specify whether or not I want to start at 0 or at 1, somehow indicating that in the terms of the sequence. Questions so far? Sequence is just a list. So I could define the terms in a sequence Here I'm defining the ith term AI with the formula 1 over I. And I've indicated that I is going to start at 1. If I want to have an infinite sequence, I just want to keep going, I'll put that up here. So just like in a sum, like we did in Calc 1, that's sigma, I'm going to do the same thing here. Start at the lower, go to the upper. If I wanted this to start at 0, I'd have a problem because what's 1 over 0? So I can't do that. But I could also create this as an ordered list. Now, here is a common problem. I've used a set brace to indicate this sequence, but sets are normally unordered, aren't they? This is a case of not having good differentiation in the notation, but still trying to understand that we're not really not treating it like a set. Some textbooks, to be pedantic, will always write parentheses instead of set braces, like we had ordered pairs, right? Now I have an ordered sequence. So sometimes you'll see set braces used, sometimes you'll see parentheses used. It's a convention of which textbook you're looking at. So when you look at online sources, you may see them indicated differently. But it's clear, if I asked you for the 73rd term in this sequence, you'd be able to say it was 1 over 73. It is not always the case that I can identify which number is the next number easily. I'm going to define a sequence, Pn. I used P because I'm going to use primes. We've already talked about this. What's it mean to be prime? It's only divisible by 1 in itself. So the first prime number is 2. Only things that divide 2 are 1 and 2. 3, 5, but not 4. Because 4 is divisible by 1 and 4 and 2. 6, can't use it. It's divisible by 2, 3 as well. But 7, not 8, not 9, not 10, 11, 13. And they keep going, right? But if I asked you what was the 100th term in this list, I'd be hard-pressed to tell you what the 100th prime number is. I don't know. I know there's a way to find out. I can just write the list out and keep going. We'll talk about how to get that list in chapter 4. But I can generate prime numbers. If you ask me for the most recent prime number, well, that's got like hundreds of thousands of digits. I have no idea what it is. I don't even know where it is in the line. So this sort of sequence, while perfectly well defined, is difficult for me to know precisely what's where, as opposed to that first sequence. Some sequences are defined in terms of other pieces of the sequence. This is a recursive definition, Gesundheit. And in order for me to use this recursive definition, I have to give you a starting point. And if I'm going to start with natural numbers, n, then I'm going to do f0 is 1 and f1 is 1. And then this formula is only going to be true for n bigger than or equal to 2. So in order for me to know what's going on in this sequence, I have to know what's already happened in the sequence. But I know how this sequence starts. It starts 1, 1. Those are F0 and F1. So F2 is F1 plus F0. F1 plus F0. And F3 is F2 plus F1. 2 plus 1 is 3. And then the next one is the sum of the two before it. 2 and 3 is 5. 3 and 5 is 8. 5 and 8 is 13. 8 and 13 is 21. And off we go. Colin, you're nodding. You recognize the sequence? Okay, what's it called? Interestingly enough, Fibonacci really doesn't tell me about this guy's name because he's Italian. Fibonacci means son of Bonaccio. His first name is Leonardo. Leonardo, son of Bonaccio, who lived in Pisa, was writing a book to convince everybody that they should use Arabic numbers, Arabic numerals, instead of Roman numerals. So he wrote a book on counting, the Liber Abaci. And he wrote a problem in which he said, I have a pair of rabbits. They are brand new, just born. One male, one female. When they are a month old, they are old enough adults to breed with each other. Gestation is 1 month. How many rabbits do I have? How many pairs of rabbits do I have? At the end, each birth always gives birth to another pair, one male, one female, every time. He's rigging this something fierce. But let's think about it. I start with one pair of rabbits at time 0. 1 month later, still only have one pair of rabbits because they've just now gotten old enough to breed. So they breed. Gestation is a month. At the end of the second month, I have one pair of adult rabbits and one pair of newborn rabbits. You've heard the phrase breeding like rabbits, right? So what happens to my adult rabbits? They get pregnant again. But the babies are too young to do that. So at the end of another month, the adult rabbit gives birth to a new set of babies. And the old babies are now old enough to breed. So I have 3 sets of rabbits. 2 breeding pairs means at the end of the next month, I'm going to get 2 more sets of babies, right? I already have 3. I'm going to get 2 more. I'm going to end up with 5. See how it keeps building like this? And he showed that doing this problem in Roman numerals was very difficult. But doing this problem in Arabic numerals was quite easy as the sums got larger. If I have a nice formula, we refer to such a thing as a closed form expression. Now, the Fibonacci sequence does not, at this point in time, have a closed form. It's got this recurrence, this recursive definition. It would be nice if I could find a closed form. There is a method to do that. We'll see it in chapter 8. Questions? Technically, my description for Pn, the nth prime number, is not a closed form. It's not a formula. It tells me exactly what the thing should be. It should be the nth prime number, but I don't have a formula to make that. So that's, again, not a closed form. But that 1 over I, closed form. What's the 213th number? 1 over 213. Next. Some closed forms are a lot nicer than others, though. An arithmetic sequence. An arithmetic sequence is of the form a plus n times d. A and d are real numbers. They can be anything, but n is our index from the natural numbers. So, wait a minute. Let's write out what this sequence looks like. If I were to start with n equals 0, I'd just have a, right? And then, when n equals 1, I'd have a plus 1d, and then a plus 2d, and a plus 3d, and a plus 4d, and so on as nauseam, right? Um, wait a second. What's the graph of that equation? It's an algebra question, people. Y'all should be able to do the algebra question. It's the graph of that equation, y equals a dx plus a, whose slope is d and whose y-intercept is a, right? If you put in x equals 1, you're at this point. If you put in x equals 2, you're at this point. X equals 3, you're at this point. This is a line. It's the discrete version of a line. It's not continuous. It's just a bunch of dots on a straight line. Now I get why they call it discrete math. This is a discrete line. An arithmetic progression is a straight line. By the way, the reason I used d for the slope is because it is the difference between two successive terms. If you subtract the smaller one from the bigger one, you get d, no matter which two you pick in a row. On the other hand, a geometric sequence looks like that, where a and r are real numbers, and n is a natural number. Do me a favor and write out the first 4 or 5 of these as well. N is 0. I'm going to start with A. What's next? AR. Then, and then AR cubed, AR to the 4th, AR to the 5th, and so on. Only the R is getting raised to the power. The A isn't changing. Why would we call this geometric in behavior? Well, yeah, the power is in there, the shape is changing. I was adding in the arithmetic sequence. I'm multiplying here, right? And multiplying from straight to square to cube, the geometric shapes, aren't they? That's why this is referred to as a geometric sequence, because we think of those powers as shapes. I don't know how to do it, a fourth power, except say, well, that's a tesseract. That doesn't make any sense. And there's no visual for that. But originally, these powers were read as square, cube, square, 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 cube, to get 2 and 3 to make 5, cube, cube, and so forth. Mind you, that's Greece 2,500 years ago, but that's the way they read it. But if I really think of this as an equation, it's an exponential equation. And exponential growth multiplies. And that's why it's a geometric behavior. So again, this is a discrete version of a graph I've already used. Questions? You will notice that I'm going with n in n, right? That means that technically these sequences go on forever. These are infinite. If I want to define a finite sequence, then from some point on, all values are 0. And I just don't care about them. But I can actually do that formally, and I say, well, then it's just a finite list of numbers. It's an n tuple, however big we want to go. I talked about ordered pairs. If I was doing more, it would be ordered triple or quadruple or quintuple, and that's why we use n tuple. So I would have a value A0, A1, all the way up to a capital N for some n, and then we'd stop. You could think of this like any word in an alphabet you like, right? Theorem in Greek, theorema. That's the word theorem written out in Greek. But it's a string of 7 letters, and we stop. That's a sequence. Theta, epsilon, omicron, rho. Oh, shouldn't be a rho, it should be a pi. Stop. That should be a pi. Epsilon, mu, alpha. That says theorem. But it's a sequence, 7 objects in a row. I could do these in binary, right? Numbers that are 0s and 1s. That's a string of numbers. It's a function onto the set 0 and 1. Every value is either a 0 or a 1. I could have an empty string, like the null set, a blank space. You don't have to write the name. Typically in strings, we indicate an empty with a lambda. I don't know why, but that's what they chose. Questions? More often when I am looking at infinite sequences, I really don't like having random descriptors. Having a closed form is much nicer. So if I have a recursive definition, I would like to convert recursive definitions to closed forms. This process is called solving the recurrence. And it isn't always trivial. Sometimes it's rather difficult. But my goal is to find a closed form. Let's start with some easy examples. That first term should be A0 equals 1, not AN. Apologize. A0 is 1. AN plus 1 is minus AN. That's a recursively defined series. That's a recurrence relation. I'd much rather have a closed form. But looking at this, that doesn't help me very much. Write out the first 6, 7, 8 terms. From 0 to 7 or 8. Write them all out. And write the index under each one. So A0, A1, A2, all the way out to, say, 7 or 8. And once I have this written out, my goal is to find a pattern of the way I build each number to hopefully write that as a single formula. But I start with 1 here, then I get a -1, then I get a 1, then I get a -1, then I get a 1, then I get a -1, 1, negative, wait a minute, those are all positive. Now, some of you have done sequences and series in other classes. If you've taken Calc 2, you did them then. But that was last semester or maybe a year earlier, so you might have to dig back in your memory banks. But let's think about this. I start with a 1. This says take the negative of that. That means to multiply by -1, right? So to get from here to here, I've multiplied by a -1. So that means that this 1 right here is really -1 times the term before it. That's -1 squared, right? I had a 1, I multiplied by -1 once, I multiplied by -1 a second time. What's this one in that same vein? Oh, it's negative the one that was before it. So it's -1 times the thing that came before. But those both have bases of -1. What do I do to the power? -1 times -1 squared is -1 to the third. I add the powers. Then this one's going to be, oh, wait a second. This is just 1 -1. This, how many -1s did I have here? I didn't have any, did I? If I'm right, what's this one? I found a closed form. AN is -1 to the n for all n. One formula to rule them all and in the darkness bind them. I found it. This sort of from examples generate a pattern is an inductive reasoning. We were doing deductive logic. I have all the patterns. Now let's apply them to this situation. Now I'm working the other way around. I have all these situations. Is there a pattern that comes out of them? So bottom up instead of top down. I would like to do the same thing here. So I again would recommend that the thing you do first is write out several terms. Let's say the first 4 or 5. And tell me what pattern you see developing. Excuse me. I didn't even bother to find out what the actual value is. I just wrote down what I did with the recurrence relation, right? Each n says take the term you had from the previous line and subtract the value n. So the value n is 1, I take a 0, subtract 1. The value n is 2, I take a 1, subtract 2, and so on. And I get this. But now I start looking at what's going on here. What's the next one? What's A5? I can jump right to this part, right? If I write A5 like this, it's going to be 4 minus 1 minus 2 minus 3 minus 4, the previous number, minus 5. I'm just going to keep adding on minus whatever the number is, yes? But isn't that the same as subtracting? What if I pull that minus sign out? What goes inside that parentheses? Positives. 1 plus 2 plus 3 plus 4 plus 5. Yes? So A6 should be 4 minus 1 and 2 and 3 and 4 and 5 and 6. I just found a formula for AN, didn't I? AN is 4 minus what goes inside that set of parentheses? Let's inductively argue our pattern. Ta-da! Now, this particular sum can be thought of as a picture. Remember, I said this idea started in Greek antiquity, and they're geometry people. I'm going to make a picture for you. A picture I'm pretty sure you've seen before. 1 plus 2 plus 3 plus 4. Look, I'm going bowling. Plus 5. I'm playing pool. Plus 6. Wait a minute. Wait a minute. This is called a triangular number because I can arrange it like a pattern of dots. It turns out that there's a formula for triangular numbers. And if we knew that formula, I could just put that formula in there and it'd be in terms of n, and I'd walk away. Do you know that formula? Maybe. Maybe not. We'll prove it later on. We'll find that formula. This process of repeatedly using the recurrence that we were given and then extrapolating from it, this inductive argument is an iteration behavior, which is exactly the same sort of feedback idea that generates fractals and was part of my PhD thesis. So I love this stuff. Questions? These examples were rigged. Really rigged. In general, this problem is actually really, really difficult in the most general terms. And it turns out that the reason this is difficult is because you can have patterns that start the same and then change. If I asked you, what's the next number in the sequence? I'm pretty sure most of you are going to tell me the same thing. What do you think is happening in each term? It's doubling. So the next one should be, it turns out that is absolutely a correct answer. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3rd, 2 to the 4th, 2 to the 5th, right? But that's also a possible answer. What the? It turns out, if you take a circle and you don't cut it, 0 cuts, you have 1 piece. If you take one straight line and you cut the circle, you can get 2 pieces. If you take 2 straight lines and cut the circle, you can get 4 and 8. But if I add this little bitty restriction and say you cannot just keep repeatedly cutting in the same place, then when you have 5 cuts, you can never get more than 31 pieces. And that's really annoying because those two look exactly the same and then they change. By the way, it is also possible to get the next number to be 30. There's a different formula that gives you 30. How? If I were asking this question, I'd be looking for this answer. But the fact that this one works is annoying as all. So really, this is a matter of pattern recognition. So I'm going to ask in this course, this would be well and thoroughly beyond the range of what I would expect you to know. But this one makes sense. Pattern recognition means we need to see a lot of patterns. Top of page 175. Here are some useful sequences to know. Patterns we see often: squares, cubes, 4th powers. Fibonacci numbers, FNs. Exponentials, right, with geometric sequences, right? Base 2, base 3. Factorials. Didn't we talk about factorials in the functions on Friday on the recording? I should know at least the beginning of those because I'll see those sorts of things. And if I see something that kind of looks like one of these, then I can maybe use that as a basis for a closed form. For example, here's a sequence. That's all I was told. Gesundheit. I'm not clearly adding the same thing each time, right? Because to get from here to here, I added 12. To get from here to here, I added a whole lot more. So this is not arithmetic. Am I multiplying by the same thing each time? Well, to go from here to here, I multiplied by 7. To go from here to here, that's definitely not multiplied by 7. Grab your calculators. Let's divide. In each of those pairs, divide the bigger number by the smaller number. So I already know that to go from 2 to 14, 14 over 2 is 7. I multiplied by 7 to get there. What did I multiply by to get here? 62 over 14? Say again?
Yeah, 4.42.
Multiply by 4.42 and it kept going. 254 divided by 62. Two 1022 divided by 254. 4094 divided by 1022. It looks like I'm almost multiplying by 4. It was just a little weird at the beginning, right? I'm multiplying by 4. Maybe I should think geometrically. If I had a geometric sequence that used 4s, it would start with 4 to the first. Four times 4 is 16. What's 16 times 4? What's 64 times 4? You have calculators in front of you. I don't want you to do this in your head. 256 times 4. 1024 times 4. Times 4, not 2. I knew that was going to catch somebody at some point. It's 4096. Hey, wait a minute. Compare these two rows of numbers. What do I see?
Subtracted.
Starting with n equals 1, not starting with n equals 0. Because I started with 4, not 4 to the 0, which would be 1. So I can say, well, maybe it's not exactly geometric. Maybe it's kind of geometric-ish. And I do see we were getting closer and closer to multiplying by 4 every time. So maybe I should start there. I am the first person to tell you that pattern matching is a wonderful job for a computer. It is my pleasure to present to you a web link in our Canvas page, the online encyclopedia of integer sequences. You give it a sequence, and it tells you where it's seen that list of numbers before. As I said earlier, it is possible to have a sequence that starts 1, 2, 4, 8, 16, 30. Here's where I've seen this sequence before. Number of divisors of n factorial. There's the list right there. Or number of compositions with no adjacent triples. I don't know what the hell that even means. Or place n equally spaced points around a circle and join every pair of points. This divides the circle into so many regions. 30. I wasn't cutting the circle with straight lines. I was connecting points. If you don't recognize a sequence after trying to look at one of our patterns, I'm going to give you problems we can solve with the references in our text. But if you come across a sequence in the wild and you're like, what the hell is this? Go here. Okay, what was the title of this section again? Oh, right, sequences and series. I'm not done. We'll pick more up on Friday. I'll see you all then.